in the previous lecture, we have started to solve some important numerical problems based on Dirac matrices. In continuation of that lecture, in this lecture too, you will see some important problems or illustrative examples based on Dirac matrices. And as I have told you that after completion of these two lectures, you will be able to solve the numerical problems based on Dirac matrices, even those problems which you have not solved earlier. The unseen problem will be solved by you after watching these videos. Okay, so let us take this illustrative example. The problem says that alpha and beta are Dirac matrices. When you say alpha, it means alpha has three components: alpha x, alpha y, and alpha z. So these are the three Dirac matrices, and the fourth one is beta. In that condition, the first problem is we have to show that alpha x equal to 1 over 2 commutator of alpha x with alpha y. Okay, this square bracket represents the commutator. Okay, in the second part of the problem, you have to show that alpha x, alpha y, alpha z is equal to 1 over 2 commutator of alpha x, alpha y, alpha z, beta with beta. Okay, and the third problem is trace of alpha dot b times alpha dot c is equal to 4 times of b dot c. Here actually the vectors b and c are the ordinary three-dimensional geometrical vectors. Okay, so in fact in this example there are three problems, and you can solve these problems very easily if the properties of Dirac matrices and the meaning of Dirac matrices are in your mind. So for your convenience, I have mentioned here again the important properties of the Dirac matrices which will be used to solve the problem. Although you have already discussed this problem in the previous lectures, but I just as a revision, I have mentioned the properties. Okay, you have seen that all four Dirac matrices alpha x, alpha y, alpha z, and beta, when they are squared, their values are equal to 1. So you know that the square of all the four matrices are unity, that is alpha x square equal to alpha y square equal to alpha z square, and that's equal to beta square, and that is equal to 1. Okay, we have seen this property earlier. Now again, the next important property which we have learnt in the previous lecture was that any pair of these four matrices anti-commute with one another. They do not commute, but anti-commute. Okay, they are anti-commutator. So you can say that the anti-commutator, that is when alpha mu anti-commutes with alpha nu, the result is equal to 0. And you know the anti-commutator is defined like that. This is alpha mu plus alpha mu equal to 0, or you can say that alpha mu times alpha nu is equal to minus alpha mu, where actually this mu and nu represents x, y, and z. It means you can say that alpha x, alpha y equal to minus alpha y, alpha x. Okay, so any pair you can take, and the different alpha also anti-commute with beta. So you have learnt in the previous lecture that the anti-commutator of alpha mu with beta is equal to 0. That is alpha mu beta plus beta alpha mu equal to 0, or you can say that alpha mu beta is equal to minus beta alpha mu. Okay, Here this mu is also xy, stands for xyz. Okay, so these properties, and apart from these two properties, you will see the meaning of this alpha x, alpha y, alpha z will be also used in this problem. Okay, so now let us start to solve the different parts of this problem. You can see in the first part I have mentioned earlier that we have to show that the matrix alpha x is equal to 1 over 2 commutator of alpha x, alpha y with alpha y. Okay, this result we have to prove. You can see using the property of this Dirac matrices, this problem can be solved very easily. This is a very simple problem, but very important. Problem is simple, but it is of great importance for your examination purpose. You can see. Let us start with the RHS. I have not written here 1 by 2. That will come after calculation. So let us evaluate this commutator. Commutator of alpha x, alpha y with alpha y. You know from the definition of commutator that this will be equal to alpha x, alpha y minus alpha y, alpha x, alpha y. Because you know if A and B are two operators or matrices, then their commutator is defined by what? This is defined as AB minus BA. Okay, so following this definition, you can write this commutator as like this. Okay, now see here there in first term there is alpha y, so that will be alpha y square. So this is alpha x, alpha y square. Remember, these are matrices or operators, so you cannot change the order. Order should be maintained. Okay, now see, you know that this alpha x, alpha y is equal to minus alpha y, alpha x. You have seen. So instead of this minus alpha y, alpha x, we can write plus alpha x, alpha y. So instead of this minus alpha y, alpha x, I have written here plus alpha x, alpha y. Okay, and this alpha y is at each. So now even in second term you can see there will be alpha y square. Okay, alpha y square. So what will be our result? You can see that will be alpha x, alpha y square plus alpha x, alpha y square. Okay, so you can see this is alpha x, alpha y square plus alpha x, alpha y square. But you know that square of this alpha y is equal to 1, and that's why this will be equal to 1, and your result is alpha x plus alpha x, that is 2 alpha x, and therefore alpha x will be simply equal to 1 over 2 commutator of alpha x, alpha y with alpha y. So this was the first part of our problem, and you can see how easily we can solve this problem if the properties of Dirac matrices in our mind. Okay. Now, in the second part of the problem, you have seen we have to show that this product alpha x, alpha y, alpha z, this will be equal to 1 over 2 commutator of alpha x, alpha y, alpha z beta with beta. Okay, alpha x, alpha y, alpha z beta with beta. Okay, again we will start to evaluate this commutator, and you will see we can just on the basis of the above problem we can solve this problem too. So let us start to find this commutator. This is commutator of alpha x, alpha y, alpha z beta with beta. Okay, so from the definition of commutator you can write it alpha x, alpha y, alpha z beta beta minus beta alpha x, alpha y, alpha z beta. Okay, now in the first term there is beta times beta, so this will be beta square, and so the first term is alpha x, alpha y, alpha z, beta square. Now again you know that this beta times alpha x, this is equal to minus alpha x beta. So instead of this minus beta alpha x, I have written here plus alpha x beta, mark it, and the remaining factors are same. Okay, again you can see this beta times alpha y, beta alpha y, this beta alpha y will be equal to minus alpha y beta, minus alpha y beta. So instead of this beta alpha y, we write minus is here, alpha y beta. Okay, again successively you can see this beta alpha z will be equal to minus alpha z beta. Okay, so this beta alpha z has been replaced by minus alpha z beta, so minus will again become plus. Okay, now in the last term too you can see this beta, this will be equal to beta square, and so our result is alpha x, alpha y, alpha z plus alpha x, alpha y, alpha z, beta square. But you know, as here in this term beta square was equal to 1, similarly here beta square is again 1, so our result is alpha x, alpha y, alpha z plus alpha x, alpha y, alpha z, and so this is 2 alpha x, alpha y, alpha z, and therefore you can write alpha x, alpha y, alpha z is what? This is 1 over 2 commutator of alpha x, alpha y, alpha z, beta with beta. So the first two parts of the problem we have solved, and you can see the solution is very simple. You can solve this type of problem simply by taking the properties of the Dirac matrices and the commutator algebra in your mind. Okay, now finally we will solve the third part of our problem. In fact, in third part we have to show that trace of alpha dot b times alpha dot c is equal to 4 times of b dot c. This result is to prove. Here, as I have told you to earlier, that this b and c are actually the ordinary three-dimensional vectors. Okay, so here we will also first of all try to evaluate the value of alpha dot b times alpha dot c. Okay, and after getting the value of alpha dot b and alpha times alpha dot c, we will take the trace, and you will see after taking trace our result will get proved. So let us try to evaluate alpha dot b into alpha dot c. As you know, alpha dot b, when you will write alpha and b in components form, that is alpha xi plus alpha yj plus alpha zk, and b will be bxi plus byj plus bzk, then when we will take the scalar product, then result will be what? You know it. This is alpha x bx plus alpha y by plus alpha z bz. Similarly, this alpha dot c will be alpha x cx plus alpha y cy plus alpha z cz. Okay, so now let us evaluate this product alpha dot b times alpha dot c. Instead of alpha dot b we can write this much, and instead of alpha dot c we will write this much. Okay, you can write it. Now take the product. Let us start to find the product. See here, when we take the product of alpha x beta x, or you can say when we will operate this alpha x beta bx on this alpha x cx, the result will be alpha x square bx cx. And when you will take the product of alpha y by with alpha y cy, the result will be alpha y square by cy. and the product of this alpha z bz with alpha z cz, this will be alpha z square bz cz. Okay. Now start to find the product of this alpha x bx with the remaining terms, that is alpha y cy plus alpha z cz. So after taking that product, your result will be alpha x alpha y bx cy plus alpha x alpha z bx cz. Okay. Now we will take the product of this alpha y by with the remaining terms, that is with the alpha x cx and alpha z cz, and that product will be alpha y alpha x by cx plus alpha y alpha z by cz. This is very easy. I am actually speaking all that steps, but that is not necessary. You can easily find the product. Okay. So after multiplying these two factors, our result is as you can see in this equation 1. Okay. Now we will actually express these matrices as a 4 by 4 matrix, because this alpha x square, alpha y square, alpha z square, and alpha x, alpha y, alpha z all are actually 4 by 4 matrices, as we have learned in the previous lecture that these Dirac matrices are even ordered matrices. Okay. So you can see I have mentioned that alpha x, alpha y, alpha z are 4 by 4 matrices and having their squares equal to unity. Okay. So this alpha x square, alpha y square, and alpha z square, all these matrices are equal, and that is just a diagonal matrix, and its diagonal elements are 1 and all the off diagonal elements are 0. So alpha x square, alpha y square, alpha z matrices are equal to this much. Okay. You can see all the diagonal elements are 1 and off diagonal elements are 0. Now we have also learnt the matrices for alpha x, alpha y, and alpha z in the previous lecture. So I am not repeating that thing, but we will write here all those matrices directly. You can see actually to evaluate the RHS of this equation, we need to find the matrix alpha x, alpha y, and again, sorry, see here. One step here we should mention that after getting this result, you can see I have not written it here, but I am just trying to explain that fact here. You know that this alpha x, alpha y, and alpha y, alpha x, this alpha x, alpha y is equal to what? This is minus alpha y, alpha x. So in these two terms will combine together, and alpha x, alpha y will be common factor, and there will be bx cy minus by cx. Okay. Here there will be bx cy minus by cx. Similarly, you can see that this alpha x, alpha z, and alpha z, alpha x. Again, this alpha z, alpha x will be equal to minus alpha x, alpha z. Okay. So these two terms will be again combined, and your result will. First of all, I am just writing. I am not writing this step, but see here, alpha x, alpha y will be common, and there will be bx cy minus by cx. By cx. Okay. Again, this alpha y, alpha z, see it, that will be equal to minus alpha z, alpha y. So here alpha y, alpha z will be common, and there will be by cz by cz minus bz cy. Okay, bz cy. And this alpha x alpha z will be equal to minus alpha z alpha x. So this term will be what? Alpha z alpha x will be common, and bz cx minus bx cz. Okay, so you can think that in this equation there are actually 6 terms. There are 9 terms, but apart from these first 3 terms there are 6 terms, and in these 6 terms, these, when we will take these common factors, the term will become in fact 3. Okay, and so we have to evaluate this alpha x alpha y alpha z alpha x, and that's why I am trying to evaluate those matrices. You know, alpha x alpha y, you know that alpha x matrix is also a 4 by 4 matrix defined like this. You can see, I will not give just a reading. You know, these are how these matrices are defined, and you know very well to find the product of these matrices. Okay, so this is alpha x and this is alpha y. When you will multiply these two matrices, what will be your result? As you know, to find the matrix product very well, so I am not giving the process here. You can do it. That will be just a time killing process. So alpha x alpha y, after multiplication of those two matrices, you will get this much. This is alpha x alpha y. This is also a 4 by 4 matrix. This is I 0 0 0 0 minus I 0 0 0 0 I 0 0 0 0 minus I. Okay, now we need to find alpha z alpha x. This 4 by 4 matrix is for alpha z and this is for alpha x, and when we will multiply these two matrices, your result will be this. Okay, you can do it. Similarly, you have to find alpha y alpha z. Okay, this is alpha y and this is alpha z, and after multiplication the matrix alpha y alpha z will be equal to this much. Okay, you can do the multiplication. Now after getting all these matrices, we will substitute all these values in the equation number 1. So alpha dot b times alpha dot c will be what? You can see the first term, not first term, but the terms in first row, you can say. The terms in this first row is what? That will be, in fact, alpha x square, alpha y square, and alpha z square. You know, all these matrices are equal, and that matrix is equal to what? That is equal to this much, you can see. So instead of that alpha x square, alpha y square, alpha z square, we will write this matrix, and that will be just as a common factor, and the remaining term will be what? The remaining term will be bx cx plus by cy plus bz cz. Again the page has been turned. So just wait for a while, that will be okay. Okay, now see. So what will be the first term in RHS? You can see this will be this matrix which stands for alpha x square, alpha y square, alpha z square times this much. Okay, and plus you can see the second term is what in that equation. In second term, you can see the alpha x alpha y will be a common factor, and bx cy minus by cx will remain as a multiplicative factor. But you know that this alpha x alpha y matrix we have obtained, this is equal to this much, and the multiplicative factor is bxcy minus bycx. In the third term, there is actually what? There is alpha z alpha x, and this is the value of alpha z alpha x, and the multiplicative factor is what? This is bz cx minus bx cz. And in the third term, there is in fact alpha y alpha z, alpha y alpha z, and this matrix represents alpha y alpha z. You have just obtained it, and the multiplicative factor is this much. Okay, and actually this is equal to what? This is equal to alpha dot b times alpha dot c. But in our problem, we have to evaluate the value of trace of this. So when you will take the trace, what will be the result? You know, trace of a matrix means what? Trace of a matrix means algebraic sum of the diagonal elements. You can see the algebraic sum of the diagonal elements of this first matrix, which I am just crossing here, will be what? This is 1 plus 1 plus 1, that is 4. 1 plus 1 plus 1 plus 1, that is 4. So trace of this first matrix is 4. Now see, the trace of this matrix, this will be I minus I plus I minus I, and that will be 0. You have to take the sum of the diagonal elements, which are I minus I and minus I. Again, see the third matrix. The diagonal elements are 0, 0, 0 and 0. So 0 plus 0 plus 0 plus 0, that will be equal to 0. Okay. And the trace of this last matrix, again you can see the diagonal elements are 0, 0, 0 and 0. So again its trace will be equal to 0. Okay. So after taking the trace of this alpha dot b times alpha dot c, what will be our result? As you have seen that the trace of the first matrix was 4. So 4 times of bx cx plus by cy plus bz cz, and last 3 terms is 0. Okay, and so 0 plus 0 plus 0, and you know bx cx plus by cy plus bz cz, this is simply equal to b dot c. So you can write that this is equal to 4 times of b dot c, and this was the result which we have to prove. So you can see in this way we have solved all the 3 parts of this problem, and I hope you have definitely understand all the concepts which have been used in solving this problem, and definitely you have enjoyed the video, and so thank you very much.